Hey everybody, welcome to Geometry with Mr. O'Shea and your first flip lecture. Today we're going to be doing 1.1, which is Patterns and Inductive Reasoning. Hopefully you guys have the packet that I handed out in class. If not, you can go on our class website and download it and print it off. You guys will have this due on Monday. Okay, so inductive reasoning is essentially reasoning, but it's based on patterns that you can observe. All right, we're going to be talking a lot about inductive reasoning and how to actually use it, and we're going to do that through a couple of examples here. Okay, in our first examples, we want to use these ideas of inductive reasoning to find patterns and actually extend those for two more sections. So our first one, we've got 4, 8, 16, 32, and then blank and blank. Recognizing the pattern, I can see that if I multiply each term by 2, I get the next term. Times by 2, times 2, times 2. If I do 32 times 2 to extend it, I'll be left with 64. If I multiply that one by 2, I'll be left with 128. So that's your first one. All we're doing is multiplying each one by 2. And our second one here, we have 384, then 192, 96, 48, and 2 blanks. Well, this one pretty similar to the first, but this time around all we're going to do is divide by 2 and divide by 2. We're going to continue that pattern going, divide by 2 again, and we'll get 24. Divide that in half again, and we'll be left with 12. So your missing numbers in number 2 were 24 and 12. Number 3 might be a little trickier. Not too bad. We've got O, T, T, F, F, S, S, E, N, blank, blank. You might be thinking that this is some kind of crazy code, but it's really not too bad. All that this one is O stands for 1, T for 2, T for 3, F for 4, F for 5, S for 6, another S for 7, an E for 8, an N for 9. That means this one's going to be 10, and the last one will be 11. 10 would be T, and 11 would be E. In that one, all we're doing is using the first letter of the next term. All right, and our last one. Got a couple of circles listed out here. So we got our first one. And all we did is cut that one exactly in half. And our second one, we got to cut that one into half yet again. And our third one, this is actually where we actually figure out what the pattern exactly is. So if you notice up on top, this one's split into 1 equal part. And the top of this one is split into 1, 2 equal parts. And the top of your next one should be split into 1, 2, 3 equal parts. So I'm going to go ahead and do that. 1, 2, 3 equal parts. So that means that my fourth circle has to be split into 4 equal parts on the top. So I'm going to go ahead and split it into 4 equal sections. And I've got it. 1, 2, 3, 4. Now this last one gets a little tricky because I have to split it into 5 equal sections. What a lot of people try to do is just go ahead and throw a line kind of like right in this spot right in here. And if they do that, you'll see what happens. I don't end up actually getting 5 equal spots on the top. This section is a lot bigger than this one here. So what we have to do is something a little bit different. Just make it equal parts on top. Go and draw out your circle. we're going to go ahead and separate the top. And now in this one, I know that I need 5 equal sections, so I'm not actually going to be able to go ahead and have a line going directly down the middle. Won't be allowed in this one. So we're going to go ahead and cut that top piece into 5 equal parts. So I'm going to start slightly off center. Or one here, and then if I cut these sections in half, you'll have one that has just about 5, 1, 2, 3, 4, 5 equal parts. And again, it should not have had one going directly down the middle. Alright, so what a conjecture is, it's basically just a conclusion that you reach using inductive reasoning. So exactly what we just got done talking about. Okay. So in our next example, we want to go ahead and we want to actually make a conjecture, right? I want to make a conjecture about the first 30 odd numbers, right? And we know that if I've got 1, that's just going to equal 1. I think the next one on your paper is 1 plus 3, and that's going to equal 4. And after that I've got 1 plus 3 plus 5. Well, 1 plus 3 plus 5 is going to equal 9. And then after that I've got 1 plus 3 plus 5 plus 7. And if I add those up, we end up getting 16. So I want to go ahead and use some inductive reasoning here. And what I notice, a little pattern pops up. If I have one term, 1 squared equals 1. In this next piece I've got 2 terms, and look at that, 2 squared equals 4. In this next one, I've got 1, 2, 3 terms. 3 squared equals 9. Hopefully you guys are starting to see this pattern here. And in this last one, I've got 1, 2, 3, 4 terms. 4 squared equals 16. So I'm thinking that if I add up all the numbers of terms and I square that, that will give me the sum. Now I can test it if I want to by extending this pattern and saying what happens if I have 1, 2, 3, 4, 5 terms. That should be 5 squared. Let's test it. Ready? 1, 3, 5, 7, and 9. 1 plus 3 plus 5 plus 7 plus 9 would equal 25. And 5 squared is 25, so our actual inductive reasoning, the pattern that we observed, is correct. So when I want to go ahead and I want to make a conjecture about the first 30 odd numbers, that conjecture is going to be the sum of the first 30 odd numbers is equal to 30 squared. Squared. Or 900. That's actually the conjecture that we're going to go ahead and pose. Alright, last but not least, we're going to talk about counterexamples. And counterexamples are basically an example for which, sorry, that's 4, for which the conjecture is incorrect. Okay, so a counterexample just kind of proves everything wrong. So if I want to make a conjecture about the 4th and the 5th prime numbers, when I know that the first 3 odd prime numbers are 3, 5, and 7, some people might look at that and say, all these numbers are just going up by 2. 3 plus 2, 5 plus 2, 7 plus 2. We can continue that pattern. So some people might think that the fourth and fifth prime numbers are actually, we've got 3, 5, 7, add 2, I'd get 9, add 2, I'd get 11. However, I want to test my conjecture always. You always want to test them. And maybe look for a counterexample that proves it wrong. And we do have one that proves it wrong, right here with the 9. 9 is not a prime number. Even though we were adding 2 and we were following the pattern that we thought we saw, you always have to test your conjectures, because 9 is the same thing as 3 times 3, which means that it is not prime. So we just found a counterexample to our claim that the conjecture, the inductive reasoning, said that, oh, all we have to do is add 2 for each one. This is an example of a counterexample. Now let's move on down a little bit farther here. We want to use this table to make a conjecture about overnight shipping price in 2003. Well, it looks like every year that it goes up, the price also increases. And $8 to $9.50, $9.50 to $11. It looks like that price goes up by $1.50. So what's the price going to be in 2003? We can just go ahead and add $1.50, and I think that the price will be $12.50. My last question for you here is, how can you find a counterexample to your conjecture, if one exists? If we continue this pattern on for 2007, 2008, 2009, so on and so forth, it's reasonable to believe that shipping will continue to raise $1.50. So maybe there isn't one. However, what if we went backwards in time and we went to 1999? We'd have to subtract $1.50, go up, right? 1999 would equal $6.50. And if we went past that to 1998, now we're at $4. And if we went further than that, back in 97, that would mean that it was $2.50. And in 96, it would have been $1 for shipping. Again, all of this reasonable belief. Now the problem lies is that if we go back to 95, using our pattern here, in 1995, it was negative 50 cents to ship a package, meaning that they actually paid you. So it doesn't really technically work. But for this example, I think $12.50 is a good answer. Right, we have one last example down here. Complete the conjecture based on the pattern shown below. The product of a negative integer and a negative integer is, well, I've got a negative times a negative, and that gave me a positive. Negative and a negative gave me a positive. Negative, negative gave me a positive. Negative, negative gave me a positive. So using some inductive reasoning, I can tell that the product of a negative number and a negative number is always positive. Alright, there's one last thing that I want to point out to you guys. You guys have a little section here called Check Yourself. Now, in that section, I actually want you guys to do example A and the problem on the bottom, example B. These two there are no videos for. Do these, have these ready to go for Monday. This is what we're going to start off with in class. I do want to draw your guys' attention to number 4. I believe on your packets you guys only have this line. Please go ahead and write in these other lines here. Okay? That's all. Have a fantastic weekend. I'll see you guys on Monday.